So now we consider subset of C2. So in this case, we would say that C2 is the vector space that we're denoting by the letter V. C2 is the set of vectors with two entries, such that each entry is a complex number. And so W is a subset. This here is a subset of C2, which is what we call V on the notation of that theorem. But these are indeed vectors with entries that are complex, vectors of length 2 with two entries. However, the entries are constrained by satisfying this equation, right? So this is a very specific subset of C2 in which the entries are constrained. They are required to satisfy in this case the equation 3x1 minus 5x2 equals 2. This is a system of linear equations with only one equation, so it's one equation, two variables, right? It's if you think of this equation in matrix notation, so this would be the matrix of coefficients would be 3 minus 5. The vector of variables here would have x1 and x2, and this would be equal to 12, right? So if you were going to form the augmented matrix, this would be 3 minus 5 and 12, and here the column really is that one number, right? So the idea here is that W is a subset of C2 such that the entries of W are solutions of this system of equations. So first we address, okay, is the zero vector part of what's the deal with the zero vector? This was not part of the theorem. Well, it is not part of the theorem, that's true. The theorem that establishes whether or not a subset is a subspace. However, the zero is a requirement for something to be a vector space. So if that candidate is to have the properties of a vector space, then that candidate better includes as one of its members. That candidate set better have 0 as one of its members. Okay, and so for 0 to be a member of W, then we would have to verify that 0 is a solution of these equations, right? And so what happens if we evaluate, so we kind of don't know here, we write an equal sign with a question mark. If we evaluate this at 0, x1 and x2, so on the left hand side of this expression, this is equal to 0, but then we would be finding that 0 equals 12, but we know that that is not true, right? So excuse me, we would then argue that 0 is not a member of W, and that would tell us that W fails to have one of the required properties for being a vector space. And because of this, excuse me, because of this, then this set also, if this is left for you as an exercise to verify whether or not if you choose two members of W, you need to verify whether or not this set satisfies the requirement of being closed under addition and closed under scalar multiplication. So I provide you here with a note. I said, you know, how about you do this as an exercise? I'm just going to comment on one of the two. You should do the other one. Consider the scalar multiplication alpha times x, alpha times a member of W being x1 and x2, so that scalar multiplication is a new vector with entries alpha x1 and alpha x2. And now consider the linear combination 3 times the first element of that vector and minus 5 times the second element, the second entry. You could easily factor out alpha, and then the expression would start looking like this. And then since we assume this is supposed to be x1, since we assume that x1 and x2 is a member of W, so we know that this expression here is going to be equals to 12. So let's write one more line. So this would be alpha times 12. However, this is a bummer because for this new vector to be a member of W, for the scalar multiplication to be closed, we would need that this right side of the equation would be equal to 12, not 12 alpha, but just simply 12. And since that is not happening here, the way of thinking of this is that alpha times x1, x2 is equal to a vector y, and we would like to see is we want to verify is y in W, and the only way that y is in W is if 3y1 being alpha x1 minus 5y2 y2 being alpha x2, if this is equal to 12, exactly equal to 12. That's the definition of being in W. That doesn't happen here. Here you're getting an alpha 12 alpha. Therefore, this set regretfully fails to pass the test of being a subspace. Let's now consider another subset of C2. These are elements, vectors with two entries, such that now the equation they're constrained to is the entries when multiplied by each other are equal to 0. We can easily check that 0 is a member of X. That's not a problem. But however, here there are other problems. And suppose we select two specific vectors in X, and these vectors are X and Y. Here, X with entries 1, 0, Y with entries 0, 1. And now let's check the sum of X plus Y. This X plus Y is a new vector, right? And this vector will have entries 1, 1. And so we can easily see that this X plus Y is not a member of X because the entries of the new vector X plus Y are entries such that they do not satisfy, right? So if we with these entries, we say 1 times 1, this is equal to 1, and 1 is not 0, and therefore these entries are contradicting the requirement for being a member of X. So while individually little x is a member of this set and little y is a member of that set, the sum is a new vector that is not a member, and therefore addition is not addition doesn't have closure on this set. This fails the additive closure requirement.